All right, so today I will be doing LeetCode. This is problem for November 9th. The problem is online stock span. Okay, so medium problem, I know one. Okay, let's take a look. Design an algorithm that collects daily price quotes for some stock and returns the span of that stock's price for the current day. The span of the stock's price today is defined as the maximum number of consecutive days, starting from today and going backwards, for which the stock price was less than or equal to today's price. Okay, that makes sense. For example, if the stock price of the stock over the next 7 days were 180, 60, 70, 60, 75, 80, then the stock spans would be 111, 2146. Okay. Stock spanner initializes the object of the class. Int next int price returns the span of the stock's price given that today's price is price. Okay, so let's define what we're trying to do. Let me go to the restroom real quick. I need to. Alright, I'm back. That's a good shit. Alright, right, what do we need to do? Return, give the span of the next price given an already list of prices. Give the span of the next price given, just give the next, okay? Parameter, input 1. All right, your inputs, right? Your only parameter is the price of the quote unquote of today's stock. Output, we're going to return the span of today's stock, saving prior information. The stock cost information. Okay, so let's do some examples. So if I put in 100 and then 80, right, my span's going to be 1 and 1, right? Because if I input this, I have 100 for the price, and that's 1. If I have 80, oh, that's less than, that'll be less than this. It does not belong to the span of the previous one, so we reset the span. Now this was 110. This would belong to, oh, let me copy this. So if this were 110 per se, this would be 2, because the previous day is underneath 110, so that makes sense. Here's the difficult part, is when we have something like, for example, they have 80, 60, 90, right? 80, 60, 90. So that'll be 113 here. Because if you take a look here, 1, 2, 3, 4, 5, 6. There are 4 consecutive days that are less than 75. There are 3 consecutive days less than or equal to 75 or 90 in here. So that would be 3. So that's the idea of it. Let's think of some pseudocode. Now the brute force solution, right? Brute force solution. Insert and then iterate backwards as long as value is less than or equal to inserted value. Return that iteration backwards. The time complexity for this, n squared, space complexity. Then you simply need to save the space, save the prior stock prices. Here, have to iterate potentially n times backwards for each n inserted value. Okay, so that's the brute force solution. That's an n squared solution, but we can do better. We can do better than that. Right now, we're doing a lot of unnecessary comparisons, and what I'm thinking is we could save ourselves the hassle and store maybe a range of some sort. For example, here I could say, I inserted 80, right? Then I'm saying, okay, if I insert anything over an 80, that's going to be plus 1, right? Now I have a 60 here. I have a 60. Okay, anything I insert over 60 will also have an additional 1 to it. But it has to be consecutive. That's the thing. So that's no better than checking every single spot. Let's think. 60, 80. Well, I know this for sure, right? Let me think. I'm thinking out loud here. 60s, 90, or 70, 90. Let's say this is 80. Since my 90 is greater than 80, can I correctly assume that everything in between will be less than 80? No, not necessarily. This could be 91, and then the span here would be 1, 1, 2, 1. So that's not exactly the answer either. So I'm looking to kind of cache the span so I don't have to go over and research it. And I'm trying to think of a way to store that hash. Now a queue, I mean a stack makes sense, right? I mean you're gonna have to, the way I see it, now intuitively there's a way to do this in O of n time. There's gotta be. Okay, let's say I insert a number here. If it's greater than 91, 91's the largest number in these inputs here, then I know that at least extends to 91. And now at least extends to 90. Well, I'm thinking of a heap here. You know why? Because if I know if it is greater than 91, and that's the top of the max heap, then what I'm thinking is that it should be greater than all of these values. So if I know that it's greater than all the max of all the values, then that should be my span. It should be the length of the heap. Otherwise, for example, if I had 90, enter another 90, I know that it's going to be greater than or equal to 90. So then I need to find where 90 is. Yeah, I mean, it definitely works. Say if I insert 90, right? And now I know that my span is 2. Okay, what if my 90 is here? And I store in the heap, 91, 3, index 3, 91, 80, 0, 61, 62, right? And then I insert the 0, 1, 2, 3, 4th element here. I'm trying to insert a 94. So I check it doesn't go to the third position. Oh, it goes to the first position, but the third position is the max, right? So I only have a span of 1 because 4 minus 3 is 1. Right? Should I be searching by index or by max value? I mean, doing the max index way kind of works. It makes sense to me. But doing it by value might make a little more sense to me. Okay, let's think of a weird example. What if I have 5, 3, 2, 5, 6, and then I insert a 1. What if I put 6 here, right? So 6, 0, 5, 1, 1, 2, 3, 4. This is 5, 4, 5, 1, 3, 2, 2, 3, and then I insert the 1, so it'll be 1, 5. Okay, so I say 6, 0. Okay, I know that I cannot go past 0. 5, 4. I know I cannot go past 4 now. 4 is like this value minus 1. That's now I know it's the max. So each time I'm grabbing, it'll be potentially, you might go through every single one, but this is let me think. This is not a very good optimization, is it? I wish there's an easier way to store, you know, min values. Like, let me just talk through it. Maybe if I talk through it, I'll be able to come up with the answer. So I just know, for example, 1. I insert a 1. I know that I must pass a 5. I must be greater than a 5 to pass this point. So it's not, my span's only going to be 1. It's not dependent on the previous number span. Because, for example, this 5, 2, 3, 5, it has a span of 4, right? 6 has a span of 1. 5 has a span of 1. 3 has a span of 1. 2 has a span of 1. But this has a sudden has a span of 4. So my question is, you know, how do I know what's underneath number or not? I don't see an easy way, because if I were to insert a 6 here, how do I know that all the numbers here are all less than 6? You know, I'm thinking of like a hash, kind of like a deal, like a hash map maybe, where I store what this range of values could be less than. So I know that yeah, but that doesn't make sense since price would be 10 to the 5th. I know that, I mean, all these values are already less than, say, 5, okay? So maybe I keep another array that's like, okay, all these values are less than 6. Like, they're less than 6, less 6, 6, 6, 6. Do I do that? Do I have the max value? I mean, certainly the max value makes sense. I can't seem to get it. But what happens if I enter like a 5 here? Then it doesn't make sense. So if that's the case, should I just do the min value? 5, 3, 2, 2. And then I insert my 6. Say, oh, here's 6 to 6. Certainly that makes sense. What happens if this is 7, right? And I insert a 6. it doesn't really help me. So, Every time I insert a new number, I'm going to have to compare all the other numbers. But if I know that the number I insert is smaller than numbers I've compared before, then I can take that in as a span, right? Or the number I insert is greater than the number I've inserted before, then I can use that span, right? Okay, so that's the idea. The idea is that I can reuse span here. 1, 1, insert that number is not greater. It's not greater. It is greater. So how much greater is it is the question. That's O(n) squared. So that's a 4. It is greater, so that's a 5. But what if I have, 1? So this comes back to 1. And then I do a 7, right? And that would be the whole thing. I'd have to go back the whole way. Wait a second. Wait. Oh, okay. So I can go back 1 and I say, yeah, it's smaller. Now when I get here, I say 6 is smaller. I go back 5 steps. 0. So 1, 2, 3, 4, 5. I say 5 is less than, then I go back 1. So I go back the number of steps that I see in the span. Okay, so that's O of n for every time I want to calculate span, but it's a lot more efficient. In fact, amortized, since we're not actually going back that many. It's O of n, but you're not repeating it O of n times. This is actually, okay, O of n insertion, yeah. And then you repeat it 10 to the 4 times. Ooh. I mean, but what if you have a case where you have 1, 2, 3, 4, 5, 6, 7, 8, 9. I answered that 9th one. What does my span look like? Well, your span will look like 1, 1, 1, 1, 1, 1, 1, 1, 1, and then here we have a 1. Wait, it should be 9, 7, 6, 5, 4, 3, 2, 1, 9. Okay, 9. Okay, then I need to go all the way back, and I just feel like there's a better way to cache this. But at the same time, I feel like there's not. But that's only O of 2 of n, right? If you're only going through all these numbers, that's only O of 2 of n. So that's actually okay. So here's my new pseudocode. How am I doing on time? 24 minutes. Oh, that's clearly my poop time. That's okay. That's it took me a while to find the algorithm, but I found it. So iterate through each number. Okay, count span behind it. Use span amount to determine jump amount. O of 2, O1 insertion, O of n, potentially O of n. But it's only O of n once if you amortize it. Once amortized. Time complexity, O of n, space complexity, O of n. Expected jump amount to check if less than. Okay, so self.spans. Okay, self.spans.pin price. Spans equal to self.spans. Spans.pin price. If spans length of spans equal 1, return 1. Else, we are going to want to length prices minus 1 while I greater than -1 if prices at I is less than or equal to price span is equal to 1. Spans at I minus equal spans at I. Okay, so we get the spans, we get the prices, we start at I is equal to that last place, and our span is 1. Spans minus 1. So, if the price is less than or equal to, right? If the price is at this point, let's say we're inserting 9, right? Inserting 9. Okay, so then we say 1. Is it greater than the price? No. Then we add the span of that one, and we minus by 1, and then so on, 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 so on. Then we get here. Is this price greater than? No. And then add the span. I minus equal 1. Now we're at minus 1. Voila. Okay. Let's see here. We're inserting 7. Inserting 7. And we are inserting 7. We go here. 1. Is it greater than 7? No. At this span, go back 1. 6. Is it greater than 7? No. Add 5. Go back 5 spaces. So 1, 2, 3, 4, 5. Is 7 greater than? No, go back 1. Ah, there we go. Now, we have 7, and we have 1, 6, 7, right? 0, 1, 2, 1, 2, 3, 4, 5, 6, 7. Okay. Oh, 8. We have 8, that's right. 8. Because there's 1 plus 1 here. Yes, we included some. Okay, what else are we missing? So now, whenever we have something greater than 7, we simply bounce back here, and that's of 1. Now, if we have something that's smaller, then we reset, but we always keep it in mind just in case. So, that is the answer. All right, let's take a look at some more examples. Let's take a look at some of the examples we created. 2, 3, 2, 3, 80, 60, 90. Okay, 113, that's correct. And let's go ahead and test 9, 8, 9. Cool. I think that's the answer. Am I missing any edge cases? Nope, that works. All right, let's take a look at the solution. Monotonic stack. So what did I do? What did I even do? A monotonic stack. So the brute force. Okay, so for each price, we want to find the most recent day that had a price greater than price. Yes. An example, it's 47. The first element we check is 46. 46, we had to look for 30. 45, which are not greater. Is 46... then all the numbers that are not greater than 46 are also not greater than 47. Which is not great. The magic is at 85. Then if we pop from the stack, we should also add the answer associated with this. Okay, makes sense. Okay, answer is equal to while self.stack and self.stack minus 1, 0. Uh-huh. Ooh. Oh, okay. So we have kind of a visual understanding here. Pop in 100, pop in 80, pop in 60, 70. So I have plus 1. 70 is less than 80. Put that in. 70 is 2. Oh, I get it. So you don't need... So. Going back to my answer, you don't need to remember all the prices. Just the prices you didn't skip over. Right, because it's you always stop at the largest. So that makes sense. Okay, that makes sense. So that was my solution, which did not exactly implement it. While self. So let me say stack. Stack and stack minus 1 is greater than or less than or equal to price. It's our span 1. Span plus equal stack dot pop at 1. Stat dot pinned price span return span. Yeah, so that is the answer. Yep, that's right. Apologies. Made a little bit of a mistake there. Stack minus 1 at 0. Try to refresh. Okay. So that's the efficient solution. Gotcha. Okay. Looks like I was able to find the answer. It took me quite a while. I'm not quite used to monotonic stack, but this is one of the rare solutions. So to reiterate, when you use a monotonic stack, you use a monotonic stack when you're looking for an ordered set of values, and you're looking for the next greatest value, and only the next greatest value. You see, I only needed to know the basically the decreasing values, and once I had basically consumed all values in between, I only needed decreasing. So I remove all the values that invalidate that decreasing constraint. So that's when you would use a monotonic stack. Now, why did I say that so complexly? Because I don't really have a firm understanding of it, so I can't simplify it. It's a fairly complicated, it's a simple concept, but it's complicated to wrap your head around when you need to use a monotonic stack. I guess it's like approaching DP for the first time. But yeah, I had a good time doing this LeetCode problem, and I hope to see you soon.